The top left plot shows a 3D probability cloud moving towards the spherical region V, while the top right shows a 2D cross-section with the probability density represented by a heat map crossing a circular boundary, with arrows indicating the local current flow. The bottom left plot shows how the total probability inside V changes over time, and the bottom right compares the rate of change inside V with the total outward flow across the boundary. The two curves are exactly equal and opposite, showing that probability is conserved. Any loss inside the region exactly matches the amount flowing out. So let's now return to our probability conservation equation. We can then use one of the great theorems of vector calculus, the divergence theorem, to turn the surface integral appearing on the right-hand side into a volume integral. In other words, we can say that the surface integral over S of j dot ds equals the volume integral over V of del dot j. Here, del dot j, the divergence of j, tells us how much probability is flowing outward or inward at each point inside the region. And if we then use this relation in our conservation equation, we find the following blue expression, and we see that we have now written our probability conservation law entirely as an integral over the same region of space V. Now, because the region V is fixed, its shape and location don't change with time, we can move the time derivative inside the integral, in which case we find the following expression. Now, if an integral of one function equals the integral of another over every possible region V, then those two functions must be equal at each point. Therefore, we conclude that the partial derivative of the probability density ρ with respect to time plus the divergence of the probability current J is equal to 0. And this equation is known as the continuity equation. This equation lies at the heart of probability conservation. At each point x, any increase in probability density must be exactly balanced by a net inflow of current, and any decrease by a net outflow. Okay, so armed with the continuity equation, let's now derive an expression for the probability density and current by using the free particle time-dependent Schrödinger equation with the potential energy set to 0, which takes the following form. If we then take the complex conjugate of this equation, which involves switching i's for minus i's, then we find the following green expression. Next, if we multiply both sides of the first expression by the complex conjugate of the wave function, and multiply both sides of the second by the wave function, and then subtract and rearrange, we arrive at the following expression. We then note that we can write the left-hand side as I h bar d by dt of the product of the complex conjugate of the wave function with the wave function itself, whereas the right-hand side can be written in the following form. If we then rearrange this so that the right-hand side is equal to 0, and then compare with the continuity equation we derived earlier, we immediately see that the probability current is given by the following blue equation, whereas the probability density is the familiar expression equal to the modulus squared of the wave function. Thus, we see that according to the Schrödinger equation, once we've determined the wave function, we can compute both the probability density and the probability current. We again emphasize that the form of the probability density resulting from the Schrödinger equation implies that it is always greater than or equal to 0. To make this even more concrete, let's look at a simple example, a plane wave solution of the following form, where p is the momentum of the particle, e is the energy, and n is the normalization constant. Substituting this into the expression for the probability density, we find the following result, which is a constant everywhere in space. And the corresponding probability current works out to be equal to the probability density multiplied by p over m. And this shows that a free particle with momentum p moves steadily through space at velocity p over m, carrying a constant cloud of probability along with it. This beautiful intuitive picture of probability flowing smoothly and remaining positive lies at the very heart of quantum mechanics. But it also rests delicately on the specific structure of the Schrödinger equation. However, there's a catch. Despite its remarkable success, the Schrödinger equation is inherently non-relativistic. It assumes that the energies and velocities involved are much less than the speed of light. This limitation becomes evident when we remember that the Schrödinger equation is based on a classical Hamiltonian with the kinetic energy term equal to p squared over 2m, where p is the momentum and m is the mass. And this simply isn't consistent with Einstein's special relativity. For a truly relativistic theory, we must start with the correct energy-momentum relation, E squared equals P squared C squared plus M squared C to the 4. And physicists quickly realised that if quantum mechanics was going to describe fast-moving particles like electrons, then it would need a new kind of relativistic wave equation. Schrödinger himself first attempted to build one, but when his approach failed to reproduce the correct fine structure of the hydrogen atom, he abandoned it and focused instead on his famous non-relativistic equation. The idea, however, was then independently developed by Oscar Klein and Walter Gordon. Starting from the relativistic energy-momentum relation, they promoted E and P to quantum operators acting on the wave function, just as we did earlier with the Schrödinger equation. Then, following the same steps by defining the energy and momentum operators, they arrived at the following equation, which is known as the Klein-Gordon equation. And you'll often see this written in an equivalent, rearranged form as follows. Now, while the Klein-Gordon equation is indeed relativistically invariant by construction, it introduced several significant problems. Firstly, the equation is second order in time derivatives, since it contains d2 psi by dt squared. As a result, in order to determine the future state of the system, it's necessary to specify both the initial wave function at t equals 0, as well as the time derivative of the wave function at t equals 0. In other words, unlike the Schrödinger equation, the wave function alone is not sufficient to fully determine the quantum state of the system. This situation is similar to classical mechanics, where Newton's second law states that the force acting on a mass m is equal to the mass times its acceleration, where acceleration is defined as the second derivative of position with respect to time. To predict the motion of a particle, it's necessary to specify both the initial position and the initial velocity. In contrast, as we've already seen, the non-relativistic Schrödinger equation is first order in time derivatives, meaning that specifying the wave function at t equals 0.
Selamat datang di live stream. W in the chat, bro. In the chat. Selamat datang penonton. Satu penonton ya, selamat datang. Kita ngerjain proposal sambil nonton video fisika.
Is enough to completely determine the future evolution of the system. However, in the case of the Klein-Gordon equation, because it's second order in time derivatives, the wave function alone is not sufficient. To fully specify the quantum state, one...
You can donate, bro. Kamu bisa donate ya. Terima kasih penonton pertama. Kemarin yang nonton cuma 10, cuma 20 orang, terus keluar semua di menit-menit 10 menit, tiba-tiba masuk lagi 5, keluar lagi. Nontonnya cuma berapa detik doang gitu, cuma 1 menitan doang kata yang nonton gitu. Ya soalnya fisikku nggak kuat bro kalau dibuat main game gitu, streaming game. Ya streamingnya cuma streaming gabut-gabut gini aja sih. Makasih ya yang udah join. Oh man, 1 orang yang nonton bro, man. Halo, chat pertama, terima kasih saya. Maksud saya terima kasih untuk chatnya ya. Bisa di donate, takonya ada di deskripsi ya kalau mau donate. Donate tako 10.000 bisa buat ngirim media sama alert. Terima kasih Ophelia, what the frick, Ophelia JB4MR Jember, I don't know. Thank you, I appreciate this. This is my first chat, but I can do none, bro. Wait. But actually, can you do none? Wait a minute. The first chat. I'm gonna pin this chat. I know there is no one gonna be watch my stream. That was crazy.
Must also provide the initial time derivative of the wave function, and this extra information cannot be extracted from the initial wave function alone. Thus, the Klein-Gordon wave function fails to provide a complete description of the system
produktif dulu. Nanti ngerjainnya
in quantum state,
produktif dulu ya.
which is inconsistent with one of the central principles of quantum mechanics, that the wave function by itself should fully describe the physical system. But this isn't the only issue. Another significant issue arises when we consider solutions to the Klein-Gordon equation. For example, the Klein-Gordon equation has plane wave solutions of the following form, and if we sub this into the Klein-Gordon equation and rearrange slightly, we find the following expression. And so we see that this implies that the plane wave solutions to the Klein-Gordon equation satisfy the Einstein energy-momentum relation. Taking the square root, we find that the energy associated with the wave function is given by plus or minus the square root of p squared c squared plus m squared c to the 4. This immediately reveals a serious problem. For every positive energy solution, E greater than 0, there is a corresponding negative energy solution, E less than 0. If negative energy states were allowed in a single particle interpretation, a particle could decay into lower and lower negative energy states indefinitely, emitting unlimited amounts of energy, something completely at odds with physical observation. However, the difficulties did not stop there. Further complications arise when it comes to the interpretation of probability. For the Schrödinger equation, the continuity equation naturally leads to a positive definite probability density, ensuring that probability is always positive and meaningful. However, this is no longer the case with the Klein-Gordon equation. To see this, we start with the Klein-Gordon equation. If we then take the complex conjugate of this equation, we find the following blue expression. Next, if we multiply the first expression by the complex conjugate of the wave function, and multiply the second by the wave function, and then subtract the second from the first, we find the following yellow expression. Next, we recognize that the first term can be rewritten as a single total time derivative using the product.
Oh, my mom calling. Wait, I need to mute.
Assalamualaikum.
And if we then rearrange, we find the following blue expression.
My mom calling.
And then we can compare this with the continuity equation that we derived. Of the following form.
Wait a minute.
If we sub this wave function into the Klein-Gordon probability density and simplify, we find the following result. And so we see that the probability density is proportional to the energy of the particle. And as we've already seen, the energy is given by the following expression, which includes negative energy solutions. And this then implies that the negative energy solutions have negative probability densities. This fundamentally undermines the interpretation of the wave function as a probability amplitude, making it difficult to maintain consistency with the principles of quantum mechanics. Probabilities within the context of quantum mechanics are supposed to represent real, measurable chances of finding a particle in a given region of space. As a result, the Klein-Gordon equation, despite its elegance, fails to support a consistent single particle quantum theory. And to make matters even worse, the Klein-Gordon equation also fails to predict the correct energy levels for the hydrogen atom, and it also overlooks key features such as spin and fine structure, further limiting its viability as a fundamental description of relativistic particles. and it was Paul Dirac who fully recognised these shortcomings. We can now understand more clearly Dirac's response to Bohr at the 1927 Solvay conference. If you recall, when Bohr asked Dirac what he was working on, Dirac replied, "I'm trying to get a relativistic theory of the electron," to which Bohr answered, "Klein has already solved that problem." But we can now see why Dirac disagreed. He had convinced himself, much as we have just argued, that the approach of Klein and Gordon was fundamentally flawed and inconsistent with the principles of the newly developed quantum mechanics. Dirac realised that a new approach was required. In particular, Dirac sought a wave equation that would be first order in time derivatives, just like the Schrödinger function alone would fully determine the system's future evolution, while also preserving a positive definite probability density and allowing the wave function to retain its interpretation as a true probability amplitude. But he aimed even higher. The equation needed to be fully consistent with special relativity, meaning that space and time had to be treated on equal footing, and so the equation had to be linear in both space and time derivatives. Dirac, often seen as quiet and introspective, had already watched several of his European contemporaries make landmark contributions. Now, he set his sights on an ambitious goal, one that would lead to one of the most profound equations in all of physics. So, what did Dirac do? Well, before uncovering the magic, just a quick reminder, if you're enjoying this exploration and want more deep dives into the ideas that shaped modern physics, then please consider hitting the like button and subscribing. It really helps the channel grow and reach more people. But now, let's get back to the story. Well, first of all, if the equation is to conform with the principle of relativity, then it must contain a Lorentz invariant expression of energy and momentum. In other words, it must apply to the relativistic energy-momentum relation E squared equals P squared C squared plus M squared C to the 4. Now, a natural start point might have been to write the energy as the square root of P squared C squared plus M squared C to the 4, and then promote the energy and momentum into operators acting on the wave function psi, where the momentum squared operator can be expressed in terms of its x, y, and z components.
Du bist echt fleißig mit deinem Spanisch, Letty, oder?
Ja, mit Sprachenlernen 24 macht halt Spaß. Keine endlosen Vokabellisten, einfach jeden Tag ein bisschen.
Und du zählst da kein Abo, richtig?
Genau, einmal gekauft und gut. Ohne Abo, ohne Stress.
Klingt verlockend. Wie viel Zeit steckst du da rein?
Gerade mal 17 Minuten am Tag.
Then, if we make the standard substitution for the energy operator, we arrive at the following blue expression. However, this is not satisfactory for a few reasons. Firstly, from a mathematical perspective, deal with the square root of an operator. Also, from a relativistic perspective, energy and momentum do not appear in a symmetric way. Dirac realised that if the square root could somehow be rewritten in a linear form involving px, py, and pz, then this might solve the problem. For Dirac, this was the crucial point. But how could he? Dirac's great insight was to write the p squared c squared plus m squared c to the 4 as a linear combination of px, py, pz, and mc squared, proposing the following form, where alpha x, alpha y, alpha z, and beta were unknown constants that would need to be determined. Then, to ensure that this is consistent with the Einstein energy-momentum relation for and beta coefficients, Dirac squared both sides of the equation. Expanding the right leads to the following beautiful expression, and this must be equal to px squared plus py squared plus